Let's look at how to use the uh, how to control the pulse widths in case of our three-phase voltage source inverters. So there, obviously, what we already know is the sine PW or the sine triangle PW. We do the modulation on a per phase basis. So what we know is about single phase sine modulation. What we'll do here is that every phase you will have one triangle, and we are going to compare that triangle with one sinusoid which is corresponding to the phase A, another sinusoid which will be 120 degree apart, and the other sinusoid which will be 240 degree apart, so on and so forth. That's what we do. So it's a per phase modulation scheme, a sine PW. Alternately, we can come up with, the people have come up with another technique known as a space vector pulse width modulation, which is doable for a three phase. It is defined only for three phase inverters. Okay. Now we look at the three-phase sine PWM for the voltage source inverters. So as I said, we'll have one triangle, one carrier. We have one carrier and three modulating wave. So this is V control 1 of A phase. This is V control of B phase, and this is V control of C phase. So together we compare them and then generate the output voltage in this case. Okay. So this is the comparison. What would happen whenever the sine is greater than triangle, in the corresponding phase we will generate a pulse. So we, if you look at the red waveform, this area, in this area, the red is smaller than the triangle, so you will have a 0 here. And in this area, the red is greater, so you will have a plus here, until again the triangle becomes larger, which is here. So over here you will get a pulse like this, and then the triangle is again smaller. Then we'll have a negative or off logic, and so on and so forth. This is how we generate the pulse. Similarly, for the B phase you will have a different pulse, and for the C phase you will have a different pulse. All of them phase shifted symmetrically in time, 120 degree with respect to each other. So we get the pulse 1 for A phase, and then we get it for B phase, so on and so forth. All of them are similar things. So you can see that corresponding to the peak of this, you have larger pulse widths. Corresponding to the peak of this, you have the larger pulse width here, so on and so forth. So we can generate the PA, the pulses for A phase, PB, the pulses for B phase, and PC, the pulses for C phase. Now we'll look at the quantification of the fundamental voltage. So for the sine PWM, the A phase voltage VAO is going to be plus VDC by 2 whenever PA is logic 1, and minus VDC by 2 whenever the PA minus PA bar is the high logic. And VAO, in that VAO would be VDC by 2 times MA times sin omega t, where MA is decided by the V control peak divided by V triangle peak, because the pulse is going to be proportional to that ratio, pulse duration. And we go by the same logic as in single phase case, where you have a linear modulation range which is between 0 and 1. So long as the sine, the peak of the triangle and the peak of the sine, if you compare, the peak of the sine would be always less than or equal to the peak of the triangle. It should not exceed. If it exceeds, it's a non what we call as the over modulation region, where the proportionality of the fundamental is not maintained with respect to the control voltage. Now we look at the alternate scheme for the modulation of your three-phase voltage source inverters, in this case which we are discussing. The idea is what we call as a space vector based pulse width modulation. The idea or the philosophy behind this is the following. So if you remember um, our induction motor or other AC motors, three-phase motors, we know that if you press three-phase voltages on a spatially shifted coils, there are three coils which are spatially shifted, and we apply a voltage which is shifted in time on those coils, which will in turn generate the three-phase currents which are shifted in time. So we have a three-phase coils which are shifted in space, and we apply three-phase currents which are shifted in time. So together that will result in, so for example, IR would result in an oscillating magnetic field in this direction, and the Y phase will generate an oscillating magnetic field in this direction, and the blue phase will generate an oscillating thing in this direction. Together they will generate a rotating magnetic field which will be in the three-phase stator. Okay, there's a rotating magnetic field B which is in the three-phase stator. Okay, so the magnetic field keep rotating with respect to time because of the spatial arrangement and the time shift. So the space vector is defined that way. So the B, which is the actual vector in space, it's in reality there is a physical vector which would be there in the space if you impress three-phase currents on three spatial shifted coils appropriately chosen. So we have B bar, which is the vector notation, which is equal to the R phase B, then the Y phase B, and B phase B, which will be the three-phase quantity. It's a three-phase vector which physically rotates in the space. Now, in the same vein, in the same line, we can think of a vector which is not a physical vector. It's a mathematical transformation or mathematical representation, a compact form representation of three-phase currents. So we are trying to represent this three-phase currents as a single quantity, which is a space vector. Okay, this is a it's an imaginary thing. It's not, it's like it's a mathematical construct rather than a physical vector. B is a real vector in the physical space. I is a mathematical construct. So we can generate a mathematical quantity which is comprising of the R phase current, the Y phase current, and the B phase current. It will be a single quantity which will represent the three of them. In a similar fashion, we can generate the V bar, which is the space vector voltage, which will represent the three-phase voltages in one go. Okay, again it's a mathematical construct. So in this case, VR in itself is a Vm cos omega t, Vy is Vm cos omega t minus 120, Vb is Vm cos omega t minus 240, and they are shifted in space by this transformation e to the power j0, which is essentially your cos 0 plus I sin 0, then e to the power minus j 120, which is cos 120 minus j1 sin 120, etc., etc. That is a space shifting transformation. So together it generates one single vector. Okay, so B, we know that it is rotating in this space. It's got a circular trajectory in space. Similarly, we can imagine the I bar, V bar, which are the mathematical construct, which also have a circular trajectory in the transformed space. Okay, so with this assumption, we'll try to understand how you can use this for modulating the inverter. So this is for sinusoids. So we have assumed that these all are sinusoidal quantities. But what if you're wanting to, because you are using an inverter which can either switch to plus VDC by 2 or minus VDC by 2 in each phase. So what will be the outcome of that? We'll have to look at that. So as we mentioned, that Vref is Va plus Vb e to the power j1 minus j120, Vc e to the power minus j240, where Va, Vb, Vc are sinusoids with they are 120 degree shifted in space time. Sorry. So Vref is a vector which is rotating with speed omega. Okay. Now we need to generate this vector, and in any pulse width modulation, what you do is to do an averaging over a TS period, right? So that's what you've done for the sinusoids. If you remember the sinusoid, what we did is that we had a fast going triangle. We said that if your triangle is too fast, we zoom it one triangle period, your voltage, the control voltage would remain fairly constant. And that's what the assumption we made. Similarly, we would try to approximate these points as close as possible to the circular trajectory, and all those points we can realize using what is available to us in the inverter. So that is the idea which we would use. Okay, so let us consider omega t equal to 60 degree. So what would have happened in case of voltage waveforms at 60 degree? One of the sign is going, if you consider Va is equal to Vm sine omega t. Okay, so we have one of the sign is going 60 degree, it is coming down, the other is coming up. Third one is going to be the negative peak. Okay, so Vr is half, Vb is half, Vc is minus 1 at omega t equal to 60 degree. So we generated that point. So this is from the A phase, it gives me plus half. B phase we get minus plus half again along this direction. C phase, this is the direction, but it is minus 1, so we get this point. Okay, so we get half minus half, we get this resultant. So you have to find out what will be the resultant of this one. So what would happen? The resultant of these two is going to be some vector along the same direction as this. Okay, but with half the magnitude. So what would happen? This Vref is in this direction. The A phase contribution is half in this direction, B phase contribution is half in this direction, C phase contribution is 1 in this direction. So the effect of A phase and B phase gives me a vector in this direction, but with half the magnitude as original. So that gives me the sum of these three, this way, then this way, and parallel to this one you have this vector. So I get this Vref. Okay, this is my Vref, and that happens to be 3 by 2 times this one, because we know that this is unit 1 and this is going to be half of that. It will be half because it is coming from these two. Okay, so I get representation like that, and we know that VAO, VBO, VCO, if you consider it in three-phase 180 degree conduction mode, that is square wave operation mode, we get that, okay, I get plus here, minus here, plus here. So VA can either be plus VDC by 2 minus VDC by 2 plus VDC by 2. So these three components we get. So VA is in this direction plus VDC by 2, and VB is minus VDC by 2, that is in this direction, and VC is plus VDC by 2. So this is in this direction itself. VB is got a negative sign, so it is away from the B axis. This is B axis, A, B and C. You note that it is 120 degree shifted and in a counterclockwise sequence. Okay. So VAB, VA, VB, VC we get. And now we'll take the sum of these three which will give me a single vector, which is Vref. Okay. So we look at the Vref at plus minus plus, this notation which represent plus VDC by 2 minus VDC by 2 plus VDC by 2, we get, okay, just let me put the by 2 here. Okay, so this is a sign which we have considered and it resulted in this vector. Now the next vector, if you look at, if you choose this one, plus minus minus, okay, so what will be the outcome of that? So we have plus in this direction, and VB is minus, that is in this direction, and VC, now in this case this is a C direction, VC would have been in this direction, or if you draw it would have been in this direction. So together the overall this would look like we have a larger vector in this direction. So this would be corresponding to plus minus minus. Okay, so we can generate, this is plus minus plus, here it is plus minus minus. Now the next one, it will be plus in one direction, a direction, let me use a different color, plus in this direction, then plus in this direction, B direction, and then you want to go in the other direction, so it should be minus of this one. So it is corresponding to plus in the red phase, plus in the yellow phase, and minus in the blue phase. Okay, so that gives me this location. Similarly, you can generate the remaining things also. Now all of them together we get 6 distinct locations which correspond to that, which will form a hexagon, and the arms of the hexagon, or this one has a length of VDC. This also will have a length of VDC. So this is our hexagonal structure. So 3-phase voltage source inverter can have any of these points which you can switch. Okay, so these are what we call as a vector locations which we have. We have 6 of them here which we identified from the square wave. Now note that if you go back to the original circuit, okay, let me go further. We have all the possible cases we have not explored. We have 3-phase 3 switches, 3 SPDT switches which can have 2 states, isn't it? So we'll have, each of them will have 2 possible states. Okay, so each switch will have 2, and we can have all the combination possible. So that will give me 8 possible combinations. So what did we miss? We saw that it can be plus minus minus, minus plus minus, uh, minus minus plus, plus plus minus, minus plus plus, plus minus plus, all those things. But it's which is this is all from square waves, okay? But it is also possible that I can have all the switches connected to the um, all the switches connected to the plus terminal, all the switches connected to the minus terminal. So what will be the outcome of that? If you remember the circuit, if you connect all the 3 nodes to the plus rail or the plus DC rail, we are going to get another neutral point like common point, okay? So all the connections of ABC load connections would come to one point. So I'll have a neutral point which is already physically connected to one point, and the other side the load would have. So what I'm trying to say, you have 3 loads and they are connected to one single neutral point N. Now the other side is connected to either plus rail, so it will be plus 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 here, which acts as a single neutral point, or it is connected to minus minus minus. So if it is minus minus minus, it is another thing. So okay, so we'll get minus minus minus. So either way, you have both the end of the loads are short circuited with respect to each other, and that gives that isolates the input side from the output side, and there is no power delivery from the DC link source to the output side, and therefore this is the what we call as the freewheeling mode, freewheeling switching states. Okay, so these two switching states are sometimes called as zero vector or zero switching states. Okay, so we identify that we have 6 active vectors which can be generated from the inverter, and 2 zero vectors. Okay, 6 active vectors and 2 zero vectors, or zero vectors meaning that they are not delivering any power from the input to output side. So together we get 8 switching states. It mind you that both plus 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 and minus 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 represent the same situation or same vector in the space. So that happens to be the center point of the hexagon, which gives me no power at all. So that is we call as a zero states, zero voltage states. The vector is only one. So there is only one voltage vector which correspond to the zero power delivery, which is and we have 6 active vectors which is corresponding to the power delivery. Okay, 6 active vector, 2 zero states, and 1 zero vector. Okay, so 7 vectors, 8 switching states, 7 vectors. Now what we will do here is that we'll try to use this and generate the Vref in an average sense. That is the idea which we are going to use. What we are going to do, we look at the Vref here. Okay, this is the point which we want to generate in space, in the space vector transformed space. Okay, so we need to generate this vector. What we have to do is that we have to approximate it using other available vector. These are the vectors which is available to us. Okay, these are the vectors which is available to us. Now as a simplicity, what we to have the minimum error, because this is the point which I want to generate. Now this is in one instance, next instance the vector would be here, the next instance the vector would be here, next here, next here, so on and so forth. which will in turn generate a circular trajectory. That's what we are planning to get. Okay, so we're going to get the slices of the circle, the points which we want to implement. Okay, so all these points is what we want to implement. How do we do that? We need to switch between the available vectors. So you look at here, in this particular triangle, we call it as a sector. In this sector, if you want to have the minimum error, the vectors which we would choose would be v1, v2 and one of this. Okay, so in order to generate vref, I'll average v1, v2 and v0 or v7 or both. Okay, so this is a general equation. The vref in ts period, so the volt second balance is written here. It's a time average of the vref in ts period. So vref can be implemented in ts period as the volt second balance of v1, v2, v0 slash v7. v1 and v2 are important. v0, we can choose that location, vector location, by either implementing v0 or v7, one of the switching state. Okay. So we get this as a general equation. So we switch it for v1 is switched for a time t1, v2 is switched for a time t2, and v0 or v7 or both can be used for a remaining time t0. Okay, so if it is both are used, v0 t01 and v0 v7 t02, that's the general expression. Now mod of v1, mod of v2, etc., all are vdc, which we already mentioned. Similarly, vref, we are the mod of that is represented by just vref without any bar notation, and the length of v0 or v7 is 0. Okay, so it's a 0 vector. It's got 0 length that correspond to 0 power delivery at the output. Now how do we realize this? So you look at one sector. Okay, this is sector 1. Let me call it sector 1. Sector 1, if you look at the sector 1, we want to generate vref. So what we do is that this is my v1 direction. Okay, I scale v1 by this amount t1. Okay, that will in turn give me a component along this direction, and we use v2 which is in this direction, and we use a scale version of that v2 t2, which will be this component. The sum of that will give me this vector vref. Okay, so essentially we have v1 t1 plus v2 t2 is equal to vref into t1 plus t2, but that is equal to ts also, because mod of v0 and mod of v7 are 0, so that will be as good as having no voltage at all. Okay, so this is the eventual equation which we'll find. From here, by solving this in the x-axis, the alpha axis and beta axis, where if you resolve them, you should be able to compute t1 as well as t2. And once you compute that thing, whatever remaining time, ts minus t1 plus t2 should give me the t0 period, which can be used to split between t01 and t02. Okay, so how do you resolve it along this one? So we'll look at that thing. So vref is the modulus of vref is vref, modulus of v1 is vdc. So along the alpha axis, if you look at the resolution, is that vref, if you look at this is the resolution, vref cos alpha, mod of vref cos alpha is the component here which is shown in orange color, and mod of vref sin theta is the component along the beta axis. Okay, now what will be the outcome? So mod of vref cos theta multiplied by ts, which is this this component, which is equal to vdc multiplied by VDC is actually V1, modulus of V1 is VDC, VDC T1 plus VDC cos 60 T2. Okay, so T2, this component is also in picture for us. This is the component multiplied by T2 should give me one component in this direction. Okay, so Vref will have two component. This is the Vref projection of Vref in this direction, and this is the projection of V1 in this direction, V1 T1. Okay, projection of that, and then the projection of this, this is the vector, you get that. So those three vector together, I get the total result. Okay, so we have Vref cos theta Ts is equal to VDC T1 plus VDC T2 cos 60. Okay, now along the beta axis we look at this direction and what is the contribution of each of them. So we know that the V1 doesn't have any projection on the beta axis, so it will be just V2 and T2. Okay, so it's just V2 and T2 here, so it's only T2 which will come into picture. So V of sine theta Ts is equal to VDC sine theta multiplied by T2, and T1 T2 can be computed from equation 1 and equation 2. And once you compute both of them, the T0, which is equal to T01 plus T02, which will be Ts minus T1 plus T2. Now, if you choose T01 and T02 to be exactly equal and half of the total period, then we call it as the conventional space vector PW. Now, what we'll try to quantify, what is the fundamental in this case. So if you look at this one, the maximum which I can achieve for this triangle is this without exceeding the boundaries. Okay, if I use the circular trajectory such that it is touching the triangle here, that is the in circle of the hexagon, and that is the maximum which I can generate without losing the volt second. Okay, so what we call as the linear range. In the linear range, we don't consider this one, and we note that at linear range at this location, exactly at the middle point, we have T0 is equal to 0. Okay, all these things would be generated either by T1 and V1 and V2. Okay, so only at that location. Everywhere else you have some T0 gap here. Okay, this is corresponding to the T0. Okay, so at the center point, at the peak point, you get T0 is equal to 0 in this case. So that is the limit. In case of the linear modulation, linear range, Vref max is equal to this length of the midpoint of the triangle, and that happens to be VDC multiplied by root 3 by 2 that we can compute. Okay, using that triangle, divide the equilateral triangle into two half triangles with the center point, you get that it will be VDC root 3 by 2, and VA peak can only be corresponding to 2 by 3 Vref here, because if you look at this thing, we know that this will have a this is in the three-phase domain. We got that it will be 1.5 times your then the actual voltage in the ABC reference frame. Okay, so in the ABC reference frame you have if it is unit one is the A phase voltage VDC, then in the three-phase domain or alpha beta domain it will be 3 by 2 times that thing. So when we convert from the alpha beta to the other side, we have to scale it by 2 by 3 to bring it back to the original magnitude. Okay, so it be a peak, which is going to be the per phase peak value, which can be computed from the 3-phase peak value, which is here. That will be 2 by 3 Vref. Okay, so Va max can be VDC root 3 by 2. Va max would be VDC root 3 by 2 multiplied by 2 by 3. So I get this cancelled. What remains is VDC by root 3. So that will be 0.577 VDC. So what it turns out is that at this point, the length of this is going to be VDC root 3 by 2. The phase voltage in the phase voltage, it can have the peak value of the phase voltage can be 0.577 VDC. So in case of your other one, the single phase or per phase modulation in the sine PWM, VA max, the peak value of the VA, the maximum value for that is VDC by 2, isn't it? Or 0.5 VDC. Here I have 0.577 VDC. In sine PWM, it is 0.5 VDC. In space vector, it is 0.577 VDC. Or we have, for the same VDC which we have chosen, we can have an increase in voltage here. Okay, so for the same VDC which you have chosen, for a given VDC, let us say we choose VDC as 600 volt, you get a 15.4 voltage, a percent boost in the output voltage. Okay, so the outcome would be a little higher, which is interesting for us. So we compare the sine and sine PWM and the space vector PWM. So the specialty about sine PWM, it's very simple to implement. So you can use it, you can generate it using a digital or analog implementation. It is pretty simple, straightforward, but it has got larger torque ripple compared to the space vector PWM, and that is actually going to be a little difficult thing. And we have less, fundamental output for a given VDC. Okay, but again there's one more advantage. The common voltage here is less compared to SVPWM. So when we come to the space vector, we know that it can only be implemented digitally because it's a little more complicated computation which is involved, and it is not so direct or not so simple as compared to the sine PWM. But as we already mentioned, for let us say if we choose VDC is equal to 500 volt, we get for sine PWM, VO max would be, peak would be about 250 volt for sine PWM, but it is going to be something more. It is greater than 250 for SVPWM. It's going to be a little larger, about 15% larger than what is available to the other one. So that gives us the advantage for this one. Also, it has got the best ripple performance in the torque. Okay, so the torque is may have a ripple due to the PWM operation, but that ripple is going to be the minimal in case of a sine SVPWM, and it is the best in that case. It can be shown that it is one of the best or near to the best case, near to the optimal case, but whereas SPWM, it is much worse. But we actually are getting this advantage with the compromise that we are increasing the common voltage in the phases. Okay, so the common voltage is a problem case if you have if you consider a rotating machine with a common voltage. What would happen is that the common voltage would actually flow through the parasitic capacitance and will result in bearing currents and shaft voltages, which will result in quick wear and tear of the motor bearings, etc. So that way it will result in increased maintenance. So common voltage is going to be a problem case in a different sense, but we get increased DC bus utilization, better torque ripple, etc. with CSVPW. Let me stop here for this inverter discussion on this video.